started then. Where are the rest of you? Jeez, this is like a third of the number of people who are usually here, which is only half the class. You know, like 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 people out of a class of 60. 15%-ish. Disgraceful. Absolutely disgraceful. Yeah, what do you think? So I hope everybody who's here can have lots of good interactions on a 9-on-1 basis with the professor. Anyway, sorry about last week. I hope everything was okay and the streaming was okay for everybody. I'm sure you heard from my voice that I wasn't really, I shouldn't have been on campus, let's put it that way. But, yeah, anyway. So, there's a test today in the afternoon. Everybody's aware of the test, I assume. Good, good. There we have the 10th person. Now we have a full class. So, are there any questions about the test before we get started? Anybody got any lingering questions that they'd like to ask? No? At the back, yes?
You only need a student here.
You will also need a computer. Yeah, but in terms of identity verification, yes, you will need your student card, but not much more than that. And since the test is being written on a computer, you probably don't need like pens and pencils and a calculator because you're sitting in front of a calculator. But if you want to bring like scrap paper to like write on, that's fine as well. Everybody got the announcement about where we're having the test? Good. It's that big lecture theater in the basement of the new building that is where the Phoenix used to be. Anyway, so I guess we might as well continue on with our topic as we were covering up until the end of last week. That good? Good. So, we had strayed somewhat from our discussion of data formats and how those formats are stored inside of the guts of the computer, and we had made some brief forays into the much beloved territory of algorithms, algorithm analysis, and approximation algorithms. Last time on this class, we had done the approximate square root algorithm as well as revisiting that problem we discussed right at the very beginning of this class. So, let's talk about a new algorithm, Pythagorean triples. Everybody, I hope, is aware of the Pythagorean theory from elementary school, i.e., for a right-angled triangle, the sum of the squares of the two sides is equal to the square of the hypotenuse. The algorithm that we are writing in this instance finds what are called perfect Pythagorean triangles. That is to say, Pythagorean triangles whose side lengths are integers or whole numbers. So, if you were to take both of these and square them and sum them, you'd end up with something that took an even square root. So, the approach that we are going to use is to use a quote-unquote brute force algorithm. Brute force algorithms are typical of sort of introductory level understanding of computer science. Well, once you gain the ability to write a brute force algorithm, you'll be, you will have come to the realization that the computer can be used to find things for you. You don't have to find things for the computer. In order to find Pythagorean triples, in this instance, we are using 3 nested for loops and an if statement. So, using your knowledge of previous classes, what would be the complexity of this algorithm? Given n is the input, right? How often is this if statement executed as a function of n? It's very early in the morning, isn't it? Any ideas? Yes.
Is it infinitely?
Infinite, did you say?
Yeah, infinitely.
No, this one's not an infinite loop because it's using for loops and ranges. If it were a while loop, you would be right because it's missing the increment step. But no, because these are for loops, that we're not looking at an infinite loop in this case. Anybody else have any ideas? How many times this if statement will be run based on this guy? What's the proportionality? How many times is this loop run? N times. How many times is this loop run? How many times is this loop run? How many times is this entire loop run in the context of this loop? Right? How many times are both of these loops executed, given that they're inside of this one? The first loop executes n times. The second loop executes n times. The third loop executes n times. So what is the proportionality? N cubed. We would say that this algorithm is big O n cubed. The trick to estimating the runtime complexity of any algorithm, basically any algorithm that's not recursive, is to see how the loops are structured, because the loops are going to dictate the runtime over time. See the degree of nestedness inside of that loop structure, and for however many loops there are in the algorithm, you take that loop which has the highest degree of nesting, right? You make the number of nestings the exponent on n, and that gives you your runtime approximation. Make sense? Good. So, so let's run this thing and see what it actually does then. So def, just going to call it Pyth for short. a in the range from 1 and plus 1, B and C, if a squared plus b squared equals c squared, print a, b, c. Good. I would actually have to run the function, wouldn't I? There. So, you can see, starting at 3, we find, like, this column, you'll notice, only counts up, right? This is the column represented by the outermost loop. This is the A column. The B column, of course, is the inner loop, so you'll notice that it will accelerate to some maximum, then reset and accelerate, increase, reset, increase, it doesn't go for a very long time before resetting most of the time, at least in smaller numbers, but that's sort of just how it goes. So the way that this algorithm is working is it is finding every possible valid solution and testing for validity, and only keeping those solutions which are in fact deemed valid. So this is, this is how it goes. But we may note that big O n cubed is not a particularly good outcome in terms of runtime complexity. We can do much better than this, hopefully, because cubed is pretty terrible. So, there are some optimizations which we can make to this algorithm which make it run more efficiently. Does anybody have any idea of any type of optimization we might be able to perform on this? And just shout your ideas out. There's no such thing as a wrong answer. Recursion? Well, recursion is not necessarily faster than loops, right? Sure, we might be able to reformulate this as a recursive algorithm, but unless the structure of the problem itself is inherently inductive or, amenable to recursion, you're not actually going to save anything by introducing recursion. And in this particular case, we wouldn't actually save anything by introducing recursion. Any other ideas? Yes.
What if we try using AND statements?
AND statements? To replace what?
Like for A in range 1, n plus 1, and for B in range n1 plus 1, and so on.
That's not precisely how loops work. The for loops here aren't even Boolean conditions. So, Any other ideas? Yes.
Like you can only form a triangle such that if the sum of the two smaller sides is less than the length of the larger side. So if you add that as a condition.
Could you repeat that a little louder, please?
Like, the triangle can only be formed if, like, the sum of the lengths of the two smaller sides is less than, like, the length of the larger side, right? You have that as a condition?
So, we could. That would be restricting the search space. Yeah. So the comment that that your colleague has come up with is, although you know, although all of these would, like, all of the possibilities that we're testing would be triangles, but not all of them would be right-angled triangles. So the idea would be to restrict the values that you're testing so that you're only testing right-angled triangles, right? So the question then is, you know, it would be really convenient if, like, we had some kind of formula that we could use, right, to calculate whether or not one of these triangles is in fact a right-angled triangle or not, right? It would be super, super useful if we had a formula that maybe we could use to, I don't know, calculate the length of the hypotenuse knowing only the two side lengths, you know? Perhaps we could use the Pythagorean theorem itself to eliminate one of these loops. So, so basically the inefficiency that we're addressing right now, the way this algorithm is currently set up to work, you iterate through every possible A and B, and for every possible combination of A and B, we're testing every possible C that exists under 100. We don't need to find it, we can calculate it, we have the formula, right? So, we can say something like, if A squared plus B squared mod 1 is floating point though. Gotta be careful. Well, this shouldn't be. Take the square root of it. There we go. And if that's the whole thing, modulus 1 is greater than some very small number, because this is floating point, remember. And then we take the inverse of that, we return the thing. Now let's see if this worked. No, C is not fine. There we go. So you'll notice that the list of numbers which has been obtained is, roughly speaking, it's approximately the same as we had in the other case. However, you'll notice in the C column we now have some values which exceed 100 as a size. If you're really concerned that it's not like inside of n, then you can put an additional condition in to reject any values of C which might be greater than 100. But if you're not that fussed about it, then we can just leave it as is. So this is, you know, this is a reasonably complicated formula. It's got a couple of things going on, right? So number one, this part of the expression, of course, is calculating C. A squared plus B squared square root. I'm then taking the modulus with 1. Modulus is an operator that works on floating point numbers. If you take the modulus by 1, what you are left with is whatever the remaining tail of the decimal is, right? So we are then taking whatever remaining tail of the decimal is, and we are testing it to see if it is greater than some small epsilon value. This is the same trick that we pulled to avoid exact equality comparison with floating point numbers. It just slightly reformulated, and we don't really have to worry about the value we're looking for, absolute value, and all of that, because this guy is that's never negative, right? Even hypothetically speaking, if you were to put negative numbers into it, the negativity of those numbers would be blown out by the fact that you're squaring them. By the time you get to the square root operation, you are always dealing with positive numbers, so you don't have to include the case of assuming that you might get a negative number in here. So we test to see if this is greater than some small value. If it's greater than some small value, we can say with confidence that it is a, it's got some remainder. In which case, in this particular instance, I'm inverting the Boolean condition with not. Now, it would work just as well to say less than and take out the not. That would have the exact same effect, slightly more compact and slightly more understandable. You see, you get the exact same result. But this is kind of like, when you're actually programming, you will very, very rarely come out with like the most compact notation the first time, right? It's like your brain will work in a certain way. You will write something down, you'll read it again, and you'll say, oh, well, that's actually, if I just make this small simplification, it makes it a bit simpler. And then, if you do that, your work is a little bit more efficient. Because although it doesn't dictate runtime in the same way that eliminating loops does, eliminating terms and expressions does, in fact, improve your runtime, albeit somewhat incrementally. So, what is the runtime complexity of this algorithm as it now stands? Given that it was n cubed, and we have eliminated one of the loops.
N squared?
It is now n squared. Very good, thank you. Excellent. That's an improvement. That's a pretty big improvement, actually. Like, if you take the number 3 squared is 9. What's 3 cubed? 27. So squared is much better than cubed, right? And that only increases as you go up. So, good. But we're not quite finished yet. There is one more thing that we might optimize away here. It's kind of a hidden condition, though. Another one of these little implicit desirable things that you may not necessarily know about. So we note quite a few of these Pythagorean triples have been printed, right? Are all of them unique? Do all of them represent unique triangles? Well, functionally, what's the difference between 3, 4, 5 and 4, 3, 5? one could say that these represent the same triangle which has had some kind of rotation or translation applied to it. So if you're looking for uniqueness as a constraint for inclusion in this list of triangles, we should think of some way to make it so that 3, 4, 5 and 4, 3, 5 do not both appear in the list. Anybody have any ideas about how you might be able to do that? Yes?
Maybe if you get a value from multiplying together, making sure that value doesn't appear again.
You could, yes. You could write an if condition that prevents this from being printed. Like you would have to keep like some kind of data structure that would keep track of all the triangles that you have generated so far. But there's possibly a way of doing this even more efficiently without having to use extra memory in runtime, right? It's actually a very simple modification. All you have to do, replace this one with an A. So rather than starting at 1 each time, we are starting at A. So basically, we're assuming that whatever the side length B is, it's always going to be at least as big as A is, right? So that makes A always at least, like, if not equal, it's, it's the smaller side. And besides, you're not going to get a perfect Pythagorean triangle with both side lengths the same anyway, so probably not anyway. So, let's try this then. So you'll see our list is a lot shorter. And we have eliminated 4, 3, 5. Not only have we eliminated 4, 3, 5, we have also reduced the amount of time that the algorithm takes to run rather than increasing, which is a good result. So, let me ask you a question. What's the runtime complexity of this algorithm? Yes, sir. It's still just n squared. So remember that in big O notation, we are working off a proportionality in the absence of considerations like constants. So in the B loop, right, effectively, we only run this half as many times, right? But half of that is still proportional to n, right? So the term contributed to the big O approximation of the runtime of the algorithm is still n. So this is a long, complicated way of saying, just because something has been classified as big O n squared, or big O n, or big O 2 to the power of n, not all algorithms are created equal. There is a very wide degree of variance within a single runtime categorization between different algorithms. There is definitely such a thing as a more and a less efficient big O n squared. Although, again, over time, it's the size of the input that's, like, the size of the input is roughly going to be approximate to this guy as n grows, right? Are there any questions about that? I just covered like, you know, pretty much that entire section, so. Let's see if I forgot anything. Did that. So, I think I've shown you this. I think I showed this graph to you guys previously, but let's just go over it once more. When we're talking the runtime of algorithms, the big O, like when you categorize an algorithm as having big O some function, you're saying that function, that algorithm increases either its time or its memory complexity proportionally to the function that's indicated. Now, you know, it can be more, it can be less, but the proportionality is there, right? So, as you can see, these are bad runtimes. These are better runtimes. This is very good runtime, right? In general, the only thing that makes big data applications work is the existence of algorithms such as this, right? So, take, for example, a company like Facebook, right? How many posts do you think Facebook has to process an hour? How many posts do you think that Facebook has to process a second? Right? Probably a very large number. Probably in the, you know, hundreds of thousands to millions, right? If Facebook required this type of algorithm in order to, you know, for example, if you like replied to a post and it required an algorithm on this scale to do that, you know, that wouldn't be practical, right? Facebook would require more servers than there are, you know, there is surface area on the planet. So many very clever algorithmic techniques are used in the back end of these types of companies in order to reduce the amount of processing that these pieces of software require. When you get, you know, when you start talking about like software on this scale, inefficient algorithms actually directly cost a company money, right? Every time you run a less efficient algorithm, you're having to process more instructions than you need to accomplish whatever task it is that you've set before yourself. Every time a computer executes a single instruction, a small amount of heat is generated, right? Heat energy. Electronic energy is dissipated in the form of heat through resistors and transistors and all of these components heating up very slightly, right? That builds up over time. Not only do you have the electricity input to the computer itself, you also have the problem of heat dissipation, which is why all of the server farms that you have dotted across the world, they've actually, I saw an interesting thing where, article where they're now taking like old bomb shelters from the 1960s and they're converting those into server farms because they're underground and therefore like much easier to cool because the ambient temperature is much lower, right? Like, you don't have to dig too far into the earth where you hit like a consistent like 11 degrees centigrade. But anyway, so efficiency matters, right? It's not going to matter, for anything you do in this class. But, you'll get to a point, at some point, where you're like, man, I'm glad I paid attention in this class and learned how to write more efficient algorithms. Because efficiency is king. Anyway. So we already kind of did all of this. Good. All right. So, just a couple of reminders about floating point numbers, which, may or may not be useful for you for the test. And then we will continue on to our next topic. So, consider for your consideration the quadratic formula. Everybody, I hope, will have seen the quadratic formula before. Consider this implementation of the quadratic formula. We have A, B, and C as our inputs. We calculate D as the square root of B squared minus 4AC. So we're basically taking this term here, renaming it D, calculating it separately, and then including that in the return statement, right? The way that this algorithm is returning the results from the quadratic formula is to give the negative, or give the positive and then the negative results, right? It gives the two solutions to the equation in the form of a tuple. So if we try this out on, regular, ordinary numbers, we get the expected result. If we include a rather large number in there, we actually get an incorrect result. 0 is not a solution of x squared minus 20 million x plus 1. So, what's gone on? Well, it turns out, you remember that problem I mentioned where very large floating point numbers will gobble up small numbers and they'll just disappear? We're experiencing that in this case. Now, the basic problem here is this square operation right here, right? This square inflates the B value to the point where it's large enough to gobble up smaller values under floating point arithmetic. Hence being problematic. So the question is, how would one avoid this type of situation? So you could use the decimal library for exact precision, which is slower but more reliable. Or you could also use an alternative formula, which is more numerically stable and does not lead to these large intermediate values. So, solutions to the quadratic equation are also related by Vieta's formula. x1 times x2 is equal to c over a. Given the solution with a larger absolute value, the smaller can then be computed via Vieta, avoiding loss of significant digits. So, if you're having problems with a formula, giving you results that might not be accurate, it is totally correct to sometimes suspect the formula itself. And it's particularly its interaction with floating point arithmetic. And what is the other thing that we never, ever, ever do with floating point numbers? Yes.
Equality.
Using exact equality comparison. Yes, thank you. Good. Are there any questions about this topic before we move on to the next? Good. All right. So, we're going to talk about a slightly lighter topic now before we dive headlong into object-oriented programming. We're going to talk about testing and exceptions, right? So, testing, of course, is our, our general term for the verification of the integrity of the algorithm with respect to its functional correctness. So we've talked about, algorithmic complexity and whether or not an algorithm is fast, and now we're going to talk about whether or not it's any good. Because, it doesn't matter how fast your algorithm is if it gives you the wrong result, right? Correctness, functional correctness, precedes algorithmic speed considerations because, you can only be so fast, but you can be very wrong, basically, So, good. So here's a program which has a bug. We have max product. The object of this algorithm is to take a series of numbers, like a series of digits, find the sequence of 12 digits inside of that sequence of digits, which has the highest product, max product. So, it goes something like this, right? You have a bunch of ones, and then some twos, right? And let's say we're doing, 7 instead of 12 because I'm lazy. The algorithm scans through the sequence of digits, finds the 7 that have the maximum product, which of course is going to be these ones, and then it returns that as a result. That's what this algorithm does, right? Except in this case, it does that for 12 digits instead of 7. So this contains a bug. Does anybody see the bug? It's okay if you don't, because we're going to spend a little time exploring why this bug is, where this bug is, etc. But no, there's a bug here. And this is the problem with software. It's often not obvious from reading a piece of code whether or not there are bugs in it, how many bugs there are in it, how difficult those bugs are to fix, and whether or not there are more bugs hidden behind the existing bugs which will have to be fixed after you fix the existing bug. This is kind of, it's like, bugs sometimes exist in trees like that, You solve one and 3 more appear. So, how does one go about detecting bugs? Well, the quickest and most obvious way of trying to find bugs is to run the program that you're trying to debug, right? Test early, test often. Basically, every single time that you have written a program and you want, every time that program has reached some kind of intermediate state, you should run that program to verify that the work you've done up to that point has been good, right? This often means, if you're working on a long function, you shouldn't wait until you're finished that function to test the work that you've done so far. When I'm writing software, I test more or less at the level of individual statement blocks. So if I write an if statement, I'll test that if statement. If I write a loop, I'll test that loop. I will test these things as I produce them, right? Sometimes it's like a few lumped in together. Basically, anywhere your your intermediate results would make sense, you should test them. There are several ways of testing. The one that's used in your assignment is the test case. There is an art to writing test cases. It is a skill. There are people whose entire careers in software quality assurance is writing test cases. There are people who write test cases for a living, and a lot more than you might think, like it's a viable career path. So, what is the essence of a test case? You have some set of inputs which must yield some specific outcome. So it is very, very important when you're writing test cases that you know what the output should be. Otherwise, how do you know if you've hit it, right? So that's test case. Another way we might have been able to detect this bug is through someone else looking at your code. It's kind of like having your friend proofread your essay, you know? Of course, I would caution people very heavily about this because, you know, I've had a lot of instances of academic dishonesty this year. So I would say probably not in my class because, you know, you don't know who you're sharing your code with. Even if you think you do know who you're sharing your code with, you don't know because people can't really know other people. You know, you have no idea what the secret sordid desires of this person you've known since elementary school actually are. You know, you don't know. They could be a psychopath that's been playing you this whole time. So don't share your code. That being said, it is a way that you can come to a more correct program by having your code reviewed. So, any questions so far? So, the goal of testing is to determine whether a program works as intended or not. The word debugging is the process of trying to fix a program in which a bug is already known to exist. I think I already explained in this class the origin of the term bug, so we won't go into that, but I was told recently on my thesis feedback comments from one of the members of my supervisory committee that the term bug, debug, and bug fix, etc. are street language and not appropriate in the context of formal mathematics. So also keep that in mind, I guess. To say bug is to be down on the mean streets of Program City. So, in general, software development follows a cyclical pattern. The bubble that's not shown on this diagram that should start it off is acquisition of the requirements of the program. In your context, that will mean reading the damn question, right? Read the question, then read the question again, and then when you think you know what the question says, read it again just to check to make sure that you know what the question says, because holy hell, I think like 60% of problems with 60% of marks lost on tests is due to people not being able to read the damn question. And if it's a test and you don't read the question, that means you can't read the question because it's expected that you should be able to. Anyway, after you have acquired your requirements, the next step is to write your program itself. Once the program is written, you must make sure that the compiler or interpreter can interpret what you've written. Is my program syntactically correct? Sort of aside from any correctness or functionality concerns. If it's not even a valid Python program, how do we expect Python to run it, right? So once you have it to the point where it's compilable, you test it to see if it works as intended. If it does not, you identify the bugs, you fix the bugs, and then, crucially, you retest to make sure that the bug is actually finished. It is of utmost importance that you continuously test the program to make sure that bugs have actually been killed. So, with testing, there are two general styles of testing which are commonly used throughout industry. It says white box, black box, but the real, the correct way to interpret that in your brain is transparent box, opaque box, right? That's kind of more what it's getting at. So, under white box technique, you are relying on knowledge of the source code itself in order to test and verify the integrity of that source code. Under black box testing, you do not rely on such knowledge. You examine software purely from the perspective of inputs and outputs, right? It's like, well, if you imagine the software that you've written as a box, right? And you put inputs into it, and you get outputs out of it. If it's a white box, that means that you can look inside and you can see how things are working inside the box. If it's black box, there's like a big piece of paper over it. You can't actually see what's inside of it, and you can, you have to judge whether it works purely on the basis of whether it gives you the correct outputs. The system that we use for grading your assignments uses black box testing. So what we do to grade your assignment is we take the function that you've written, we provide it with specific inputs which have known outputs. We test to see if your program produces the expected outputs. In our case, the outputs that we are testing your software against are generated by an instructor's solution to that problem, right? So for every problem that we give you, we have ourselves, secretly, behind closed doors, an algorithm that we have written which we believe implements the problem as stated. In order to generate a test case, all we have to do is pick some inputs, pick some inputs in an intelligent manner, of course, run our instructor's solution, capture the output of that instructor's solution. That becomes the thing we're testing for with the black box testing. So, one important thing to note here, both black box and white box testing requires a clear statement of the requirements of the program in order to be any good, right? We require a clear specification. Otherwise, what are you testing for? You don't know, you're just testing, right? So let's begin by talking about black box techniques. So we are not relying on knowing the program's source code or any details about the program, right? It's being examined purely on the basis of inputs and outputs. Black box testing and test cases are more or less the same idea. Now, of course, if you're doing white box testing, you will often want to run the program as well, and in order to run the program, you have to run it on some inputs. But test case generation is generally a black box testing concern. So, good. You guys are probably tired of this slide by now, but our software design principles. Our code should be modular, it should decompose into smaller pieces, and then be recomposed into some kind of working program. Each of our software modules should be self-contained, achieve a clear purpose, and you should be able to reuse them. In addition, we have the principle of abstraction, where it should not be necessary to know the internal details or workings of a function or class in order to use it. You should be able to get by simply on whatever the documentation is. You shouldn't need to know how the instructions are laid out or know anything about it really, except what it does. Black box testing plays into these software design principles. The more highly modularized your software is, the more it is possible to test those individual smaller modules, verify them individually, then put them together, and then test that as well. That's known as integration testing. The idea of the black box software module is the idea of an abstract software module. You do not see what's going on inside of it, therefore you can abstract that away. So, modularity enables better black box testing. So, let's say you have a piece of software, right? Let's say, it's Pong. Let's say you have a number of software modules inside of this piece of software, Maybe it's like, CPU player, user, the ball, and the boundaries of the game, or a score. Let's have scorekeeping. Right? Roughly corresponding to the different things that the Pong game does. Wait, you guys might not know what Pong is. Does everybody know what Pong is? Anybody not know? Okay, two people. Okay. So you know that video game, the very, very simple video game where you have like a field and a little paddle here and a ball that like you have to hit it back with the paddle and it goes like that and you have to, and if it gets past it, you get a point. That's Pong. Anyway, so if you're testing a piece of software like this, right? Let's say we were testing the CPU player's code, right? You provide some inputs to it, you take a look at what the outputs are, right? You test that module, right? This is known as unit testing, because you are testing an individual unit, right? You would perform unit testing on this unit, that unit, this unit, and that unit, right? Testing the individual pieces, that's unit testing. Integration testing would be testing the whole thing. So, while it increases drastically the reliability of individual software modules to perform unit testing on them, you know, if an individual module passes unit testing, then you know it's, you know, it does its job. The problem is that when you're writing software, you're taking lots of little units and smacking them together and building something larger out of it. That is a process undertaken by human beings, and it is a process during which mistakes can be made, although through the use of rigorous software design philosophy, you should be able to minimize the degree to which that is done incorrectly, you know, by stating exactly in the documentation what the individual modules do and how they are to be used, what they expect, what they produce. It is still possible to make errors when putting the whole thing together. So, it is not sufficient to test the individual modules of software program. You must also test the entire whole of the software program. This is known as integration testing because you are testing the integration of the individual software modules. Does that make sense? Any questions? Good. These next few slides, we're just going to talk about a bunch of different types of testing that you should be aware of. So, regression testing. It sometimes happens that you have a bug, right? You fix that bug, and then you keep working on the project, and then the bug comes back, you know? The bug came back the very next day. The bug came back. You thought it was a goner, but the bug came back. It just wouldn't stay away. Regression testing is what you do when you want to verify that old bugs haven't come back, right? And this is what that's what it's known as when a bug comes back. It's called regression because your software is regressing to a previous, less correct state. So, the biggest thing that you should do when you're writing test cases, never throw a test case out, right? You should retest old test cases that you used to find specific bugs in order to, you know, verify that subsequent modification you've made to the program hasn't reintroduced a bug that you had previously. So, if you want to do it very, you know, rigorously, you have two test cases, one that fails if the bug is present and another that passes if the bug is fixed. Keep both of these around after the bug is fixed, and this way you can detect regressions. So, this is a way of making sure that your software only makes forward progress and not backwards progress. Let's see. A developing trend inside of software as a discipline is the idea of continuous integration testing. I've mentioned software repositories here, haven't I? You guys remember me mentioning repos? Maybe? Maybe not? Everybody's looking at everything but me? No? Okay. So, a software repository is basically a program that holds on to your program for you. Overwhelmingly, the most popular repository program at the moment is Git, G-I-T. Essentially, what Git does is it holds on to previous copies of your software, basically like a checkpoint system, right? When you've made, and it's up to you to actually create the checkpoints. It doesn't do this automatically, but if you're coding, and you accomplish something, or you're going home for the day, or you're breaking for lunch or something like that, you commit everything you've done to the repository, right? You send it up, you upload it to a server, and that server is like, okay, I got it. It is possible to have local Git repositories, as well, but the real advantage, the thing that's really made repositories shine in the current software environment is that you can have fairly large teams of people all sharing code in a structured manner through a repository. Once it's uploaded to a server, you can have several users accessing that code in various ways, like you can set permissions and restrictions and all of that. And, the code can be controlled in that way, and it can be checkpointed so that if, little Tommy can't code, makes some modifications to the code base which completely break everything, all you have to do is roll it back to a point before those modifications were made, and then you restore your code to a more correct and working state. So, continuous integration testing is the reason I'm explaining this business about repositories to you is it's not possible to understand what continuous integration testing is doing unless you understand this concept of a centralized project repository, right? So, what continuous integration testing allows you to do is it puts a step in between, Johnny Can't Code's computer and the centralized database. So, when Johnny Can't Code sends bad code, what the repo will do is it will stop it coming in. It'll say, okay, I'm going to run you first to see if you're good code or not, and only if you're good code, I'll let you into the repository. So, so it takes it, it compiles the code, it, executes the code over some test cases, and the code has to pass those test cases in order to be added to the repository. So, unless, and of course, Johnny will get a message that your code failed because it's bad, and then hopefully Johnny No Code will code up better code, and then maybe it'll pass the test. And he'll probably write code that's still wrong, but at least passes the tests. And as long as you pass the tests, that's at least some way toward correctness. So that's the idea of continuous integration testing. If you decide to take Computer Science 1XC3 with me next semester, we have a lab where we show you how to set up continuous integration testing on GitHub. Anybody taking 1XC3 next semester? Nary a one of you. How disappointing. You should take it. It's a good course. It's actually my favorite course. Anyway, so here's an example of what that looks like on GitHub. If you try to put code into the repository and it does not pass certain checks, it will be rejected. You can't add it to the repository. So, good. Any questions about any of that? So let's talk now about developing edge cases, or developing test cases. That was a bit of a Freudian slip. So, when we're developing test cases, there are certain cases that you should test that you may not pick to, right? It's not just a matter of picking random numbers inside of the input page. Generally, what you're trying to hit with these types of test cases is you're trying to hit the exact boundary of loops and the exact boundary of if statements. So, you know, if you have a piece of code, you know, if x is greater than 3, you know, do something else, right? In order for your test cases to fully test that program, your test must hit, like, you must write at least two tests that exercise both of those branches of the if statement. Because, you know, if you don't actually run the else case in your testing, what happens if, like, there's a bug in it? You won't find it. And then you'll ship it, and then you'll get, you know, a 2-star review on whatever it is, you know? So you have to try to run every branch of the of any if statement. Similarly, with loops, you should try to, loops are a little more complicated, but a good case that you should run with loops is the case where the loop is never executed. Because the loop might not even run if the condition is if the condition is false, right? These are while loops in particular that we're talking about. So, given that the loop might not even be run, if your code relies on it being run in order to instantiate a variable or something, then you might end up with an error from that loop not running, which could again give you a 2-star review on the App Store. So you want to test basically anything that's not been specified as, you know, a restriction on the input range, right? In Python, this actually becomes very, very complicated very quickly because of the nature of Python, right? It's like, in Python, anything can be any type. In other languages, the input data type to a function, the type of an input to a function is fixed. So, if it's an integer, it can't not be an integer. In Python, it can be literally anything. So, you know, if you wanted to thoroughly test Python code, you would test all of your inputs. You know, how does it behave when they're integers? How does it behave when they're floats? How does it behave when they're tuples? How does it behave when they're strings? How does it behave when they're dictionaries, right? This is why serious people don't use Python, because it's, you know, at best it has type annotations, which aren't even binding, you know, but at any rate. So, even within data types, it's good to test the various edge conditions that can exist inside of that data type itself. Like, take, for example, the integers. Things behave differently when the input is 0. Things behave differently when the input is negative, right? Is a negative value an accepted value in this case? If you don't know that, you should, right? For other data types, like strings, you want to test a string containing one character, a string containing no characters, right? Lists, one element lists, empty lists. And when you're testing subsequences, which is that max product algorithm that we were talking about at the beginning of this topic, you want to test a few things, right? So if you're looking for a subsequence, right, it's good to have that subsequence somewhere in the middle, because that's sort of your nominal test case, right? It's good to test that sequence being at the very beginning, and it's good to test that sequence being at the very end. If you've messed up how the loop is to be constructed, if you're only testing the middle, you'll probably miss it. The edge conditions of the loop will show up at the extremities, right? And this is also true if you're not even considering subsequences. Like consider consider a search algorithm, right? So we've got a search, and we're, going through every element to see if it's the thing we're looking for. If you've got an off by one error where, you search, everything inside of this segment of the loop, but you miss this one, that's a bug. But you won't see the bug unless you write a test case where the thing you're looking for is in that location. If the only test cases you have place the value you're looking for in these locations, then you'll never find that bug, and that might be a problem, right? Because that means your search doesn't always find the thing if it exists, which is a violation of the property of search algorithms. Make sense? Good? So that's what we mean when we say edge case, right? It's like, another term for it sometimes is corner case. Good. So, let's return to our max product problem. So, good edge cases for this max product algorithm that we were discussing earlier, the case where the input is the smallest that it could possibly be, right? If the input is as small as it could possibly be, there should be only one solution, right? Just, the product of all 12 of those digits, right? We should also test to see the minimal output. The smallest possible output for this algorithm, it will be 0. The maximum will be 9 to the power of 12. So both of those should have representation inside of our test cases. We should also test in this manner, having substrings at the beginning and the end of our input range, right? So, with our algorithm as given, if we use the following as a test case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, the result that we acquire from this is 121,927,680. But if we examine this algorithm, first of all, which sequence of digits in this case corresponds to the maximum product? Who can tell me? Yeah?
Isn't it the ones at the end?
Yes, at the end. From here to there, right? Because if you were to take it from here to here, you would include the 1, 2, and the 3, which is, of course, lower. You want to, like the max product algorithm is basically find that bracket with the numbers with the most number, you know? Anyway. So, since this is a numeric algorithm, it's reasonably easy to just punch that into your calculator and see if that actually is the case. And it turns out that it's not. It turns out that if you enter 7 times 8 times 9 times 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9, you get, as a result, 182,891,520, which is a different number than the number the algorithm is giving us. So, we know, as a matter of fact, that we have found the bug. Something about this test case has activated the bug. And, as your esteemed colleague noted, it probably has something to do with the fact that this is placed at the end of the string. So, a very, very useful thing to do when you have found a bug is to try to find out how it was calculated. If you know how it was calculated, then you know what the problem is, right? So, unless the algorithm is very wrong, some subrange in this number, or in this sequence of digits, was selected erroneously as having the max product, right? So, if basically, not a bad way of going about solving this bug is to test other sequences inside of this, and there aren't too many of them actually, to see if we can reproduce this number. That will tell us whether we have found, that will tell us what this algorithm is actually returning as its result. This will give us information which we can use to solve the bug. So, just out of the guess, we can say, well, maybe it wasn't too far off of this original one, right? So rather than doing these guys, let's try doing these guys, just one off, right? 6 times 7 times 8 times 9 times 1 times 2 times. There we go. And oh look, we have a match. So, by attempting to find the bracket that this number derived from, we can say with some degree of certainty, the bracket that this algorithm is using is the bracket that's one to the left of the one that contains the actual answer. Question? Yes, that's the solution. Yep. So, your esteemed colleague has pointed out that if we modify this, you said to add one, but you know, this is mathematically the same thing, right? If you modify this 12 to an 11, then you do in fact get the correct answer. So what's actually happening here, the structure of this algorithm is basically, I'm going to do it with like a lower number because I don't want to do all of those. So let's do it with 8 and 4. So the way this algorithm works, right? It takes the first one, right? It takes the first element in the array. It counts out the length of the bracket, and then it computes the product. And if that product is greater than the current maximum product, it saves it as the maximum product instead. This is exactly the same way that you remember that temperature flowchart example we did way back in like the first or second lecture? It's essentially the same like maximum keeping track of mechanism. So, after it's computed this one, it then examines this one and calculates a bracket, examines this one and calculates a bracket, etc. Right? Now the problem is, in order to do that, it determines a subrange of these which constitute the valid starts of subranges, right? So, by subtracting 12 here rather than 11, what it's effectively doing is it's stopping one short of the starting number for the range wherein the answer is contained because it's at the end, right? Because really, this is the correct answer, like that's the correct starting point and range. So, if you modify that, just change it to an 11, this algorithm then works as intended. Does that make sense? Any questions about that? Good. All right, let me just make sure I didn't skip anything important. So, in this particular instance, we had an advantage, which was this is a numerical problem, and we can therefore use our calculators to verify what the output should be. This is not always going to be possible. You are certainly going to run into issues, like you're going to run into problems in the future, of course, which you can't just enter the calculation on your calculator and expect everything to work out. Rather than check like hand. So what we call your calculator in this instance, we call it an oracle. This is again software engineering terminology or computer science terminology. So you know, if you go back to ancient Greece, there were oracles who knew the future, and they made prophecies. And essentially, the idea of an oracle in computer science is that which knows what the correct answer to this algorithm should be. So when you're calculating what the answer should be on a calculator, you are using the calculator as an oracle to gather what the correct value should be and then comparing it. It's not always possible to have an oracle, unfortunately. Like, you have one in more cases than you would think, and, you know, it's often possible to just, you know, construct what you expect things to look like and then test for that. But sometimes it's not possible. In such cases, you can construct test cases which check for the consistency of results between operations of the same algorithm. I'd like you to take a look at this test case here for a moment. Both of these results should, like this, should be true, right? Because if you take a subsequence and you add 1 to the end of it, that 1 should never be included in the max product, right? Because, you know, it's 1. Anything would be more useful. It also doesn't modify where the correct bracket should be, right? Except to make it not at the end of the string anymore. So, if you were to actually run this and the bug were still present, this would come out false, right? Because in this case, it would find the correct bracket, unlike in this case, which is the case from before, right? Because, you know, basically, the correct answer would be located inside of this bracket, right? Rather than this one. Cool? So much for black box techniques. Let's talk about white box techniques. White box techniques rely on a knowledge of the program's source code. This can take several forms. It can also take the form of diagnostic software. So you can have software programs that diagnose other software programs. Some companies have a formal process of code review where code written by anybody is subject to review by senior members of the development team, which is, you know, a bit like having your code picked apart by, you know, experts. So this is much more probable in companies which have their own stylistic, like, it depends on the company that you're working with, you know. Some companies will have particular ways that they like the code written, right? And if you're not complying with that way that the code is written, then they'll be like, no, you need to fix the code so that it looks like everybody else's code. This can be a very good practice for ensuring that code is, you know, consistent and readable across multiple employees with varying personalities. But, you know, it's also an expensive process. And it takes a lot of time because somebody actually has to read your code. Whereas black box testing, if you set it up in an automated fashion, you can run it in less than a second, right? So when your code is reviewed, it is examined for A, programming best practices, B, potential inefficiencies, and C, common vulnerabilities. We'll be talking about one particular common vulnerability when we talk about databasing later on in this course. So, best practices can mean, you know, well, you know, in some languages, it's very, very possible to shoot yourself in the foot, you know. For example, a programming language, most programming languages don't require each line of the code to be on a separate line, like in Python. A lot of languages use the semicolon operator, or the semicolon character, to distinguish different statements from each other within the code. Now, you know, whether or not you are actually putting one statement on each new line, that might be something that a senior engineer would say, fix your code so it's easier to read, you know? It's like, why are you doing this? Stop doing this, you know? We put the curly braces on the next line in this house, sort of thing. It's actually kind of funny. There's, in the sort of software programming meme culture, there's a war that goes on between people who put their curly braces at the end of the if statement or on the next line. You know, it's like, it's not an issue that comes up in Python, of course, because Python doesn't have curly braces, but it's like, if versus if like that. That's the fight. That's the fight that's going on. But you know, so it might be stylistic stuff. It might be just to get your code to be readable by other people who work at the company and have different expectations. Generally speaking, the older people get, the more set in their ways they get. So like they expect things to be done in a particular way, you know, because they're you know, their brains have started calcifying, sort of, you know, pre-fossilizing before they even get in the ground. But, I shouldn't be too mean to old people, but that's okay. We're all Zoomers, except me, right? And old people, like people even 5 years older than us, are completely terrible and should be seen with disdain. Yeah, I'm a millennial, by the way, in case anybody was interested. I'm a little older than I was. Anyway, what am I talking about? Ah, yes, white box. So, code review tools are also very, very important. I'm more familiar with this in a C context because, like, in my 1xC3 class, we actually go through these things, and I actually teach these tools, and I'm not precisely sure what the same tools would be for Python, but you know, this course doesn't require it. It just mentions it, so there you go. But there are software programs which will automatically analyze your program for common vulnerabilities. In the case of C++, there's a program called CPP check. You put your program in, it says, you have made this mistake, this mistake, and that mistake. And it's, you know, extremely valuable to know this information because otherwise a lot of those would just be bugs. There are software packages that you can use which check to make sure that all of your testing runs every line of code in your program. Like you can run a program that will watch your program as it runs and annotate your source code with the number of times each line of code was executed, which is kind of cool, you know? That's, you know, if you're into statistics and stuff, it's a very cool, that's called GCOV. There are other software packages which will tell you how many times your functions were called, tell you which functions called which other functions and how many times your recursive functions recursed, and all kinds of stuff. Like, it's, if you're, and you know, and this kind of review is not just for the purposes of it, like functional correctness either. If you're picking a place to optimize your source code, any optimization that you produce is multiplied by the number of times that optimization is executed. So what it makes a heck of a lot of sense to take portions of your source code which are run the most frequently and focus your optimization attention on those, right? How do you know which parts of your source code are run most frequently? Well, you can either use your brain and try to intuit that information from the mystical majesty of the universe itself pouring its cosmic radiation into your brain. In which case, if that's your testing methodology, then I might recommend trepanning as a way to increase that. But if you're an analytical scientific mind, then you use a tool to find out for reals and how, get an actual quantified number on how many times each line of code is executed. And there are tools that do that. So knowledge of the existence of those tools is what separates real software developers from people who are just pretending to be software developers. So, anyway, tools very important. There are also code review methodologies, formal code review methodologies, which can be very time consuming. Ask me about that one because that's basically my thesis, my PhD thesis is a formal code review methodology. So, very briefly, software can be modeled mathematically inside of formal logical systems. You can demonstrate logical properties using logical proof, mathematical proof, so you can prove that your software has certain properties or doesn't have other properties, like correctness conditions, or safety conditions, or any number of conditions. But using formal mathematics requires people who know formal mathematics. It's a very advanced skill. You're basically looking at someone like in a PhD range of education to be able to even perform this work in the first place. And, it's just a very costly and time-consuming way of going about it. Even if the level of verification that you get out of it is the strongest level of verification that's possible, because you have an actual mathematical proof of correctness. There's only a handful of applications that are sufficiently advanced to require that type and style and level of proof. Intel does a fair amount of it, verifying the integrity of their chips. So, bugs in software can be fixed with software packages. Bugs in hardware cannot be fixed because it's in hardware, right? You print it and it's done. You can't go into the chip and perform surgery on it after it's been printed. That's not how physics works. So, Intel, and AMD I'm sure as well, spends a very, they spend a lot of money verifying the integrity of the chips. Because, as expensive as it is to do that, the consequences of having a bug come through in a processor, far exceed the cost of, a team of PhDs all performing mathematical analysis of the circuits, right? Make sense? Hopefully. So, a couple of important terms. Code coverage. Does the test case, or does the set of test cases exercise all lines of the source code? We've already talked about this a bit. If it does not, then it should. Again, if you don't exercise every branch of the source code, how do you know that there isn't some bug lurking on line 58 that you didn't exercise, right? Static analysis. Static analysis is it's a category of algorithm static analyzers. What static means is that it analyzes the program without running it. If it requires running of the program in order to produce its results, then it's dynamic analysis, not static analysis. But the tool that I mentioned, CPP check, is a static analysis engine on C and C++ programs that does things like check to make sure that you're using things inside the bounds of arrays. Stuff that the C compiler itself doesn't check for. So things like using variables after they've been freed from memory. A lot of this stuff is kind of like baked into Python's compiler. A lot of just kind of structurally the way Python works, a lot of these types of considerations don't come up because Python does check for them. Of course, because Python is checking for them each time, because it's an interpreted language, this makes Python a slow language. C is a very fast language because it doesn't do this type of checking. You can do this type of checking if you want, but it doesn't sort of enter the main stream of how you program with the language. And it certainly doesn't affect runtime. Unless it's an error that you found that you didn't find, that will affect runtime. Good. Any questions before we talk about debugging? Good. So, once testing has shown that your program doesn't behave as intended, you identify the bug and then fix it. In order to do so, you require two things. Number one, you need a test case that reliably fails. Number two, you need to try to understand the internal state of the algorithm. Don't be afraid to play around with a failed test case once you've found it. As we demonstrated with our previous example, if you have a test case that fails on a particular number, it will often, it's often very, very informative to push that number a little ways, push it a little ways more, push it a little ways now. Okay, now it's correct. So somewhere between here and there, it goes from being incorrect to correct. That allows you to narrow down the scope of where the problem is, right? So, but before we even get there, it's very, very important that you have a test case that fails reliably. If you've ever looked at bug reporting systems on the internet, where users can suggest bugs to developers of whatever, a lot of the time a user will report a bug, and then the developer will say, could not reproduce. What this means, normally, is that the bug was, the developer thinks that the bug was specific to the computer system of the person who reported the bug, and not a problem with the software itself. Because, if it were a problem with the software itself, the developer would be able to reproduce the bug, right? But because the bug couldn't be reproduced, it's I have nothing to work off of to solve this problem, so, Good. So to understand the internal state of an algorithm, we have basically two main methodologies, right? The first is our good friend, the print statement, also known as performing a trace, right? This is the quick and dirty method of getting your program to produce some kind of result that you can view, right? You just put it right there in the program, run the program, view the results. This is an extremely powerful and simple way of debugging a program. It's not as sophisticated, but it will suffice for most situations, actually. so long as you're using the print statements like consistently and correctly. Often the problem that you will have with printing statements, like using print statements, like insofar as this will fail, right, using print statements, there are basically two ways that it fails. A hard failure is a failure to capture the relevant information itself, in which case add more or different print statements to capture the data that you need, right? The other way that using print statements will fail is more of a soft failure, in that you can definitely get an algorithm to produce more information than you could possibly sift through to find the problem, right? It's possible to capture too much data using print statement, you know? If the bug that you're looking for is somewhere inside 100,000 lines of debug output, that's not useful, right? Although that's often the situation that you'll find yourself in, believe you me. So the alternative to this is a debugger. Now, the thing that's really nice about Python Tutor is that it's a debugger, right? If we were to categorize Python Tutor as a tool, it would be a debugger, right? It's got its limitations, but it's really good from what I've seen. So a debugger integrates with an editor to visually inspect the source code and internal state as a program is running. Now, this is slightly different from the way that Python Tutor works. What Python Tutor does is it runs the program, logs all of the internal states, and then outputs it so that you can scroll through on a timeline. Like, it's not actually executing as you scroll through the timeline, right? It's just saved all of the execution. In a sort of proper debugger that you would have attached to the IDE, you would actually, the program would be running and paused at particular points, right? So, the most important feature of a debugger is the so-called breakpoint. Breakpoints are a very important concept. To set a breakpoint inside of a program is to designate a line of code at which the program will pause. And it works, very much like watching a video, It's like you're setting a point at which the video will pause. You can sometimes even rewind back through it. You can step forward through it as well. The analogy to video breaks down a little bit. It's like stepping frame by frame through a video, because you're stepping line by line through the code. And then at a certain point, if you've gathered what you want to know, you can let it run again, and it will come back and pause when it hits the same statement again, right? And you can remove the breakpoint, set other breakpoints while things run. So, to use this for Python, well, VS Code will also have it, but the IDE which Python prefers is idle. It's built into all Python installations, and you can run it by typing idle 3. Let's just see if that actually works. Do I have it? Nope. Okay. Well, I guess that's not as true as it seemed, eh? Probably I didn't install Anaconda. I just installed the direct Python libraries on my computer, but anyway. So, idle gives you a 3-panel layout. You've got your source code, you've got a running instance of the Python interpreter, and you've got a debugging pane, right? The debugger includes debugging controls, as well as a view of local and global variables. This is basically not too dissimilar from the way the Python tutor works. Make sense? Good. So, so let's talk about exceptions. So far, we haven't actually talked about any coding. You know, it's been all just these meta concerns about coding. So let's talk about exceptions. This is error handling. So, here's something to think about. Let me just write this. Zip. Right. So, let's suppose, pardon me, let's suppose that you had a function that returns the maximum number in a list of numbers. What is the, what output should we produce if the list is empty? Yes? Sorry? None, that's one possible, yeah. That's not a bad one, but, you know, it has its problems, right? So, here are some possibilities, right? We could return 0, but 0 might actually be valid output if, like, all of the numbers in the list are negative except 0, right? You could return infinity, you could return not a number, or a none type in Python. These are okay, but if the result of this function is being used in another calculation, you're going to have to check to make sure that none wasn't returned. This actually starts to break down the principle of modularity. The thing that we want from software is that as few strings are attached to it as possible, right? If you have a function and you have to do a lot of work just to put input into it, and you have to do a lot of work just to get output out of it, that work should be done inside of the function, basically. False, returning false is kind of the, that's been our way of handling this type of situation in this class so far. But it has the same problem, right? So, consider a bound function, right? The difference between the maximum and the minimum in the list. So we have max and we have min, right? This is a fairly simple function. We would want to keep it this simple, right? If max and min have the possibility of returning false if the list is empty, you basically have two options. You either check that condition before you hit this line, or you check the outputs of both of these to see if they're possibly false. Either way, you're adding a bunch of if statements, right? Which you don't want, because you want to keep things nice and clean and modular. You could do it this way instead. This is with the if statements in. Here's a similar problem. What should happen if you pass a string into integer conversion, one that isn't actually composed of numeric digits? Should it return 0? This is not what it actually entered. Should it return false? False is not an integer, right? What should it do? Well, here's a question. What does it do? Enter a number. No. We get dun, 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 an exception. In this case, a value error. Over the course of the next half an hour, we're going to see how one goes about dealing with errors, because they can be dealt with, and we're going to see how you, even you, people sitting in this class, can create your own errors. We're going to learn to be problematic. So, exceptions allow Python to deal with situations where it tries to execute a statement that isn't well defined or violates some condition. The terminology that we use is that exceptions are raised. We raise exceptions. When an exception is raised, this interrupts the normal flow of execution. There's actually a whole process behind this known as the unwinding of the call stack. So, exceptions are handled by exception handlers, right? So, you can kind of think of it like, if we have a function, and a function sitting on that function, and a function sitting on that function, and a function sitting on that function, right? Let's say that, there's an exception handler here. Exception handler. And an exception happens in this layer of the cake, all right? What happens is it busts off this it busts off this layer, it busts off that layer, it busts off that layer until it hits an exception handler, and then it handles the exception, right? This is known as the unwinding of the call stack, but that's, that is a quick analogy. Basically, when an exception happens, it's a very similar process to when a return statement is hit. Unless that exception has been handled, it'll take whatever it's taking in as an exception and it'll quit everything until the exception is dealt with. Good. So we have handled exceptions and we have unhandled exceptions. Any error that you have seen so far, any error that you've produced as you've been traveling along your programming journey, these have all been unhandled exceptions, because if they were handled exceptions, you wouldn't have seen them, because they would have been handled, right? So, let's see how we can handle exceptions, shall we? Let me just open up a new thing. Not a folder. So, x is equal to int input, enter a number func. So, enter a number func. No. Error. This is where we were before. Try except print well, you didn't have to be mean. Enter a number, punk. Yes. Well, you didn't have to be mean. Otherwise, I guess we should print this in as well. You entered this. Print. Congratulations on being compliant. There we go. Enter a number. No. There we go. Enter a number, 7, and it does the thing. So, structurally, here's what's going on. In order for an exception to be handled, the thing which produces the exception must be placed inside of a try block. Right? So, any of the code which might fail needs to be placed inside of a try block. The except block is executed upon receipt of an error. So, when we enter no, for example, or anything that's not an integer convertible on this line, execution is immediately broken and passed to the beginning of the except block. And it prints the statement and then it goes on with its life. Note, the rest of this block is skipped, right? An error here prevents the rest of everything in the try block from executing. That's important to know. And furthermore, the stuff inside of the except block is not executed if there are no errors received here. Notice that it didn't say, well, you didn't have to be mean when 7 was entered, right? So it's like, this is what you're trying to execute. This is what executes if there's an exception. Does that make sense? In structure, it's not a million miles different from an if statement. Cool. So, another thing, so this is like a catch-all except statement. I've been told by people who know Python programming better than I do that using except to like catch all exceptions is a security vulnerability somehow. So generally it's preferred that you try to write your exceptions for the specific types of exceptions that you're expecting, right? In this case, the only thing really that can go wrong here is the integer conversion. That produces a value error. So, you can specify the type of error that the except block handles using a value error. You could even say, you know, there we go. You can use multiple of these as well. Except 0 is print. Congrats, you broke the universe. No, the internet. You broke the internet because it's more memey. All right. So in this case, right, I've added this statement here, which will result in a 0 division error if the number that the user enters is 0, right? So, you know, if we enter nothing, it still works. If we enter a non-zero number, it still works. Oh, except that it doesn't actually print the number that you want. That's, all right, there we go. There we go. Now, if you enter 0, rather than failing out on a 0 division error, it tells you that you broke the intent. So this is like an if-else block. There are many of these types of errors that you can catch, and we're going to review the most common ones. As soon as I see that I didn't miss anything important in the slides. So, here are a common list of exceptions, which you've probably, to be honest, encountered already, but let's see what they are and what they do. Index error. When you try to access something outside of the bounds of a list or a tuple, you will be confronted with an index error. The index you have requested does not exist in this data structure. That's an error. Type error. When you're applying an operator to something of the wrong type. I produced one just a few moments ago by attempting to concatenate an integer to a string. Type error. Incompatible types in operation. Value error. When the function or operator is applied to an object is the right type, but is otherwise wrong for some reason. So, if you're trying to convert a string to an integer, but it's not actually composed of numeric digits, that's a value error. If you're trying to, take the square root of a negative number, for example, that would be a value error unless you've got a library installed that deals with imaginary numbers. Generally, like the thing I'm trying to say is the negative numbers are generally considered to be outside of the domain of the square root function, so that would be like a value error and a domain error are basically the same thing. Not implemented error. When a function has not been implemented, this is basically a thing that a developer might leave in code to make that code syntactically correct, but if anybody actually tries to use it, produce an error. Recursion error. When the maximum depth of the recursion has been exceeded. Runtime error, some error that has occurred but isn't classified elsewhere. And to be honest, I've never actually encountered one in the wild in Python. Something like your computer running out of memory would show up as a runtime error, right? Errors that are sort of injected into your Python program by the operating system would be of this type, I would say. And then, of course, our old friend zero division error, because dividing by 0 is something that can't happen, not in a computer. That's one of the rules. That's rule 17, thou shalt not divide by 0. So, good. So, you yourself can have hold of this power. You can produce your own errors. All you need to do is use the raise keyword and specify the name of the error. Very, very simple. Anytime you use raise and then an error name, that produces an error as if it were produced anywhere else, right? And will be handled as if it were, as if it were anything else as well. So, for example, raise value error. Raises a value error. Raise index error, etc., etc. If you want, you can include an error message as well. This is an error message. And it will include that error message inside of the statement of error. This is not required. You don't have to do that on assignments or anything. It's just, for your education. Because, this is hypothetically an educational class. But yeah. Any questions about that? Error handling is pretty, not too bad. Yes, sir?
What about syntax errors? Will those be considered an exception?
Let's see how it handles it. Right? Let's produce a syntax error. Like let me think. It's actually hard to produce one without Anyway, oh, I've got one. It's an array, but I've left off the end bracket. It prompts me for more. All right, what happens if that's in a file? There you go. Syntax error, unexpected end of file while parsing. So, you'll notice that this is the same format of error that we've been dealing with previously. So, this is an exception that's internal to the Python parser compiler apparatus, right? Unexpected end of file while parsing. Right? It's expecting that end bracket to come, but it hits the end of the file first. I don't think there's in theory any reason why you shouldn't be able to produce a syntax error using raise. Let's try it. Raise syntax error. Yeah, you can just raise syntax errors. Python's using its own exception handling system consistently within itself as well. You had a question?
Yeah, so is raising an error what is happening in the background of when I write a program and I don't include that last parentheses? Is it within Python to raise that issue to me?
Yep. Yeah. The mechanism that I just taught you to raise exceptions is the same mechanism that Python uses to raise exceptions for itself. So, for example, index error, right? Lists are a class in Python. So one of the things that is built into its class definition is, it keeps track of how large the list is, what the valid range of addresses are, right? And it performs a check, like an if statement, before it allows you to access anything to make sure that the thing you're trying to access actually exists within it. And if it doesn't, it raises an error, and then that is the error that you see. But it uses that same raise if statement construction that you are now seeing in front of you. Does that make sense? Some languages don't. In C, if you try to access data beyond the bounds of an array, it will just give it to you.
What would it give?
Like whatever values are contained at those memory addresses, which is probably random junk garbage data, but it's happy to give it to you. because you're supposed to check your own gosh darned array bounds if you're programming in C. So Python does this type of checking for you. Any other questions? Those are good questions. Okay. Well, we really only have one more thing to talk about, and I think then we'll let class out because, you know, hard to get into object-oriented with, you know, only 5 minutes or, you know. Well, I suppose we could, like, take a stab at it, but there's a test today. Anybody object to us letting class out a few minutes early? No? No? Nobody objects? Okay. All right. The ayes have it. But first, let's talk about assert statements. So, assert statements are very similar to raise statements, where in a raise statement, if you wanted to test something and then raise an error based on that result, you would use an if statement, right? Assert basically builds the if statement into the construct itself. So you say assert some condition. If that condition is true, no error is raised, and the program continues on. If the condition comes out false, it raises an assertion error, a specific type of error that's specific to assertions. So assert statements are used pretty prolifically inside of the auto grading software that we use. So I'm going to explain how the auto grading software works now. So Jupyter, right? Basically how it works. When we write a Jupyter notebook, have you ever noticed all of those like blank little cells at the end of a question? Ever wonder why they're blank and why you can't do anything to them? Because they're locked. Those are all of the test cases, right? So, and I think they like leave a comment in them saying this is a test case, this is a test case. Sometimes they do, sometimes they don't. But anyway, so basically what happens when we receive your assignment is there's a step that Jupyter takes where it reinserts all of the actual test cases into your assignment document, right? Those test cases will often contain assert statements, most of the time, in fact. The assert statements are basically, on one side of this equality, we have your function being run. On the other side of this equality, we have the result that we're looking for. And this is like an approximation of how things work because things have become more complicated because people figured out how to break that system because in Python it's apparently it's possible to overload this operator so that it always returns true, which effectively completely destroys the autograder by always returning true for everything. But anyway, yeah, that was fun when we figured that one out, that some person publicly posted that you could break Jupyter in that particular manner. Fortunately, all of the TAs are great brain boxes, and they were able to think of ways to thwart those efforts. Anyway, so each one of those boxes has a certain point value that's associated with it, right? And that point value is also hidden. What the auto grading step does is it runs every code cell in the whole assignment in sequence, including those hidden test cases which have had the tests put back in, right? If an exception occurs during the running of that test case, you get no marks for that question, or for not the question, sorry. You get no marks for that test box, that test case specifically, right? And if no exceptions happened during the running of that box, then you get however many points that box is worth. And we use assert statements to see that, you are correctly, that the outputs match the inputs as we, as we've determined using other methods. So, yeah, so that's how it works. The exception, like exceptions and exception handling are, an integral part of how the autograder works. And, there are also like some questions where we're testing you on your ability to raise like particular exceptions. So like what we do on our end, in the back end, is we write like try catches, or it's called try catch in other languages, try except blocks that like are watching for the correct types of errors being produced on your part, and then not returning an error if it's the correct type of error, but returning an error if it's not the correct type of error, and then that error gets picked up by the test case itself and gives you the marks or not. So yeah, anyway, any questions? All right then. Monday's class we'll be talking about what was it? Object-oriented programming. See you guys at 2.